So let us now talk about the second problem, which is switching between processes. How to regain control of the CPU when a process is running. And this is done by one of two approaches. First one is a cooperative approach, which is basically you wait for system calls, and in a cooperative scheduling system, you do not regain control of the CPU unless you get a system call or an illegal operation of some kind to take place. So you do not try to basically stop any application from running as long as they are running. Um, Basically, I mean, as long as they're doing processing on the processor, you're not going to stop the application and you let it run until you get a system call. The second ways for a non-cooperative is a non-cooperative approach where the OS takes control, and this is how most operating systems operate. Um, and the way you do that is you use a timer interrupt to regain control. Now, this timer interrupt it's different from the system calls because it's basically the when a process starts running, the operating system starts ticking a clock, and each process gets some time on the processor, and when its time is over, there is a timer interrupt, and then the operating system, if takes, I mean, kicks in now, moves the to kernel mode, stops the application, moves to kernel mode, and either decides to continue running this application or to run a different process. So now that the operating system has regained control, whether cooperatively or via a system call, or more, so or via timer interrupt, a decision has to be made whether to continue running the current running process or switch to a different one. And this is done basically by the scheduler, which we're going to cover actually a part of it this week, like in the next few slides, and part of it in much more details during the next couple of weeks. Actually, I think it will only be the next week. So if the decision is made to switch, the operating system then executes a low-level piece of code that is called context switching. And context switching, what it does is that it basically saves the registers of the running process, and makes sure that its current state is saved, so that when it runs once more, when it's turn to run, then it will actually start from where it stopped. It will just pick up from where it stopped. So if we're looking at how things are actually done now with this extra level of complication, you basically at boot, you initialize the trap table, you remember the addresses of the different syscall handlers, and you remember the address of the timer interrupt. And then you start an interrupt timer, you start the timer, and you interrupt the CPU in X milliseconds, basically, or microseconds. It's actually mostly microseconds, not even milliseconds. So you have a timer, you have a process A starting, you have a timer interrupt now. So you save the registers of the process A to the kernel stack of A. You have a kernel stack for A now. You move to kernel mode and you jump to the trap handler for the timer interrupt, and you handle the timer interrupt. Okay. You call a switch routine, which is basically your scheduler, which saves the registers of A to the PCB, to the process control block, to the process structure of A. You restore the registers of B from its PCB, from its process control block, from its process struct of B. You switch to the K stack, to the kernel stack of B. You return from trap into B. So the trap here is basically your timer interrupt. You are now in the hardware. What happens is that you restore the registers of B from the kernel stack, you move to user mode, and you jump to B to process B's program counter, and you start running process B. So what happens when during a system call a timer interrupt occurs? Because you might be doing a system call, you might be trying to read or write a file, you might be trying to do something that is not, I mean, you're no longer actually, so if timer interrupt occurs while you are in doing a syscall, a syscall is in basically something that is outside of the application, right? It's something outside of the user mode. It's something outside of the process. It's basically something in the actual hardware, or in the actual that the actual operating system is doing. So if you interrupt it, what should happen? And this also is the case if you are handling one interrupt and another one happens, which might be the case. So there's the disable interrupts and mechanisms, and there are locking schemes to protect concurrent access to operating system data structures. Because one very dangerous thing is that, I mean, if you overwrite some of the data that you need in the kernel stack, for example, if you overwrite some of the data that you have in the registers without saving the registers, these are all issues that you need to handle. So there are two ways to do that. One of them is to disable the interrupts, and the other is to have some locking schemes. And by locking schemes, I mean that when you're running some parts of code, and someone asked me about what atomic operations are. Atomic operations are basically operations that you do not allow to basically be interrupted in any way. So, and these operations are very, very common in computer science. So suppose that, for example, I mean, this is not operating systems anymore, but I'm just giving an example of an atomic operation. Suppose that you are basically withdrawing money from your bank. So this is a very atomic operation. The bank does not want you to withdraw the money, and then if power failure happens and then they lose this transaction, so you have withdrawn $10,000 from your bank, but oh, power failure happened before we wrote that transaction to our bank account, to our banking system, meaning that, well, we just gave you an extra $10,000, because when you check your balance next time, you will not find it. So this is an example of an atomic operation. Another example, if you are the person putting money into the bank and you're putting 10,000 hard-earned dollars into the bank, and basically a power failure happens, and the bank does not update your account with this $10,000 that you have just given to the clerk, or that you have just put into the ATM machine, and next day you check your your banking statement and you don't find your $10,000 because, well, a power failure happened. These things cannot be allowed. So we have the notion of atomic operations that cannot be broken into parts for many reasons. And one way to enforce atomicity is using blocking schemes to protect concurrent access to operating system data structures. And atomic operations is something that you will study in databases, in distributed systems, in operating systems. They are basically a function of any system that communicates. Locking schemes basically does not enable any any other operation to touch some of the data structures that you are trying to operate on. Okay, it's basically, it's a lock. It's like as if you lock this data structure so that no one can have access to it. And once you're done with that, you have to unlock it. And this is also something that you do in parallel programming. So assume that the CPU is running process A when a timer interrupt occurs and the system moves into kernel mode. Which of the following is true, assuming the scheduler has decided to switch to process B? Pick your choice.